Welcome everyone to part one of the WARRIP webinar series titled Superpave Mix Design Method for Asphalt Mixtures. Next slide, please. My name is Susie Chan and I'm moderating the session today. Next slide. We've planned to go for 60 minutes with time for questions. Next slide. We would love to have your input, so see here on the slide how to submit your questions. Now, we're all coming from various locations, so fingers crossed all our technology works. We also have Catherine from WARRIP joining in for technical support. Next slide, please. Our presenter today is Dr. James Grenfell, Principal Professional, Sustainability and Resilience, WARRIP. Okay, let's get started. We'll now be hearing from James.
All right, good morning, everybody, depending on where you are. What we're going to run through today is an introduction to the Superpave method for mix design. This is a two-part webinar, so we'll go into a bit more detail and some examples in the next session next week. There's also the possibility to delve into a bit more detail should questions arise from this particular session as well. So bear that in mind when considering any questions. But today what I'm going to do is to go through the components of an asphalt mix, talk about Marshall mix design versus the Superpave method, and then we'll look at the Superpave method in more detail in terms of material selection when considering bituminous binders and aggregates, talk about designing an appropriate structure, then talk about designing the binder content, and then at the end touch upon moisture sensitivity of mixtures generated through the Superpave mix design method. So first of all, I'm going to talk about the components of an asphalt mixture. And the first thing that we need to talk about is bitumen behavior. Essentially, bitumen is a temperature susceptible material. So it's stiffer at lower temperatures and softer at high temperatures. It's viscoelastic, so at high temperatures it acts as a viscous fluid, and at lower temperatures or low temperatures it tends towards the behavior of an elastic solid. In its normal service condition, asphalt acts in an intermediate temperature range and therefore has characteristics of both viscous and elastic behavior, hence viscoelasticity. We also need to consider that bituminous binders age, and when they age they oxidize, and this leads to age hardening. Now we'll quickly talk about aggregate behavior. So there's obviously lots of different types of aggregate. Most of the time we're talking about natural aggregate, but we could also be talking about processed aggregate, so aggregates taken from quarries, crushed, synthetic aggregates such as blast furnace slag, and even recycled materials. So things like recycled crushed glass can be used as aggregates. So we need to consider whether they've got enough shear strength to resist repeated loading applications. And this depends on internal friction which is provided by the aggregate. So basically we're designing our mixtures to have enough shear strength to resist against the traffic applications, and in order to do that we need to have some internal friction between the aggregates. So they need to be generally cubical and have a rough texture to provide more resistance, and we tend not to like rounded aggregates in our asphalt mixtures as they don't provide that internal friction. So when we mix our bitumen and our aggregate together, we create asphalt mixtures. Asphalt mixtures are what we are building our roads out of. We're designing them to be resistant to permanent deformation or rutting and fatigue cracking, and potentially low temperature cracking. So that's one of the things about Superpave that you might notice a bit more as we go through. Obviously, it's come out of the US. Low temperature cracking is much more of an issue in the US than it is in Western Australia. So why do we go through a hot mix asphalt design process? What we want to try to do is develop an economical blend of aggregate and bitumen that meets our design and function requirements. Historical methods of asphalt mix design include the Marshall mix design, which I'm sure most people are very familiar with. Others include the Havim method. So the next thing that I want to talk about is just to discuss a little bit about Marshall mix design method versus Superpave. So obviously Marshall mix design is probably the most widely used mix design method, and it's commonplace in Australia. It's got a proven track record in terms of producing quality hot mix asphalt to produce long-lasting pavements, and the method allows an engineer to determine the optimum binder content to be added to a specific aggregate blend to make sure that the resultant mix meets the desired properties of density, stability, and flow. And so the methodology involves aggregate selection, bituminous binder selection, then sample preparation, including compaction, which is done with this device on the right, which is a Marshall hammer, stability determination, density and void calculations, and then finally the determination of an optimum asphalt binder content. So it has a number of advantages. It's designed to stress the entire sample rather than just a portion of it. It allows fairly rapid mix design development. It produces densities that are reasonably close to field densities. And the density and void properties of asphalt mixtures are relatively easy to measure. And also the equipment required to develop a Marshall mix design is relatively inexpensive and easy to operate. It does, of course, have some limitations. It basically involves an impact compaction method, which isn't a direct simulation of how asphalt mixture is densified in the field. The stability measurement isn't an exact estimate for shear strength of hot mix asphalt. Unconfined testing isn't necessarily representative in situ stresses. And there's also a number of empirical test parameters which aren't directly related to pavement performance. Also, it doesn't identify mixes that are easily compactable under traffic loading and doesn't simulate mixture densification. So then if we're to consider how Superpave differs from Marshall, I guess the first big difference is the compaction method. So the Superpave method uses a Superpave gyratory compactor or a gyratory compaction method, which is a hydraulic kneading action, which is much closer to the types of compaction method that are used in the field. It also differs in terms of a few other things in terms of, say, specimen dimensions, avoids analysis approach, and also in terms of its overall specifications. I was going to say, typically the optimum densities developed with the Superpave gyratory compactor require less bituminous binder than the Marshall methods. So let's delve into a little bit more about how and why the Superpave mixed design method was developed. So essentially, Superpave is standing for Superior Performing Asphalt Pavement, and it's come out of the Strategic Highways Research Program in the US, which started in 1987 and involved a vast amount of research. It's underpinned by a performance-based system which specifies bituminous binders and also the mineral aggregates to be used. It helps perform the asphalt mixture design process, and also helps to allow analysis of pavement performance. So the total system involves binder specifications, using what were at the time new binder physical property tests. There's a series of aggregate tests and specification requirements. It then has a hot mix design and analysis system, and there's also some underpinning computer software that helps to integrate the different components. So the Superpave mix design method has been designed to handle the unique weather and traffic conditions of any geographic site. I guess the main proviso is that well, it's developed for the USA, so therefore we need to be mindful of how some of these requirements translate to Australian conditions. But essentially it integrates materials selection and mix design procedures based on a particular project, construction project's climate and design traffic. And so there's a number of tests performed at different temperature and aging conditions that can more realistically represent the conditions that are seen in service pavements. So there's testing that's carried out to understand the properties of the mixture during construction, so such as the rotational viscometer. There's tests that are carried out on the binder to understand potential rutting performance, and also to understand potential fatigue performance. And there's some tests that are carried out which are probably much more applicable to US conditions, but to understand low temperature cracking. And that includes binder testing using direct tension testing, and also the bending beam rheometer on aged bituminous binders. So when we're considering construction and rutting, we tend to be looking at the binders in a relatively sort of unaged state. So during construction, unaged, the rutting, we start to consider short-term aging, or the aging that would be seen during mixing and laying, which we tend to simulate by RTFO aging, so rolling thin film oven aging. And then by the time we're starting to consider the fatigue cracking and low temperature cracking performance of the binders, we need to consider long-term aging, which we carry out with a pressure aging vessel, a PAV. So the Superpave mixed design method is based on laboratory compaction using the Superpave gyratory compactor. So this device, as I mentioned before, is essentially applying a kneading action to the asphalt mixture. So one note is that the Superpave gyratory compactor can be used to design mixtures that do not exhibit classic tender mix behavior and do not and so we're trying to develop a design that doesn't densify dangerously to low air void content, particularly under the action of traffic. And there's been a lot of testing and analysis to underpin the direct relationship between the Superpave gyratory compaction and field performance. So the primary objective for this compaction method is to establish an appropriate amount of binder content in the resultant mixture or the design mixture that can simultaneously satisfy the rut resistance requirements and also the fatigue cracking requirements for any given traffic level and any environmental conditions. So now let's just move on to the different steps of the Superpave mix design method. So essentially there's 4 main steps. The first one is material selection in terms of bituminous binders and aggregates. The second step is to design an appropriate aggregate structure. The third step is to undertake compaction testing with the Superpave gyratory compactor to determine the design binder content. And the final step is we are required to undertake some moisture sensitivity testing in terms of a tensile strength ratio test, which I'll get onto the end, towards the end of the presentation. So first of all, we need to be selecting our binders. So in terms of the bituminous binders, they are selected based on environmental data in terms of temperature ranges and also in terms of traffic level and traffic speed. These binder requirements consider permanent deformation, fatigue cracking, and also low temperature cracking. And as part of the SHARP program and the overall Superpave system, some performance grades have been developed. So these are for bituminous binders, and they have developed a performance grading system, PG grade, that are related to the 7-day average temperatures and the minimum anticipated pavement design temperatures. So typically when we have a PG grading, we have 2 numbers specified. So the high number is the 7-day maximum pavement temperature, and the low temperature is the minimum pavement temperature. So then we define our PG grading. For example, if the 7-day average maximum pavement temperature was 70 degrees C, and we had a minimum pavement temperature of -10 degrees C, the binder that we would choose would be a PG 70 -10. There's also been the development of a number of algorithms to convert air temperatures to pavement temperatures. The first one is the SHRP high temperature model, which is considering that high temperature, and it's calculated according to the equation there. So it takes into account the air temperature, but it's also taking into account the latitude of the section to be constructed in degrees. So obviously, again, this is very applicable to the US. We need to be mindful of what that means in Australian terms, and a bit later on I'm going to discuss about how the performance gradings of the binders that are used in the Superpave system compare with the common binders that we're using in Australia. The selection process also has a low temperature model, which is again dependent on air temperature and then the depth in the pavement where you're considering your design temperature. And there's underlying software that can be used to help calculate the binder grade that you should be using. So there's a note here that a commonly used grading in the USA is PG 64-22, and that, as I explained before, means that the 7-day average maximum pavement temperature would be 64 degrees C, and the minimum 1-day pavement temperature would be minus 22 degrees C. So just to put the PG grading into context in an Australian setting, so if we were to consider C600 binders, they would fall somewhere in the PG 70-16 range, or potentially the PG 70-22 range. If we were to consider a C320 binder, that sits somewhere in the PG 64-22 range, and a C170 would sit in the PG 58-22 range. So as we get stiffer in terms of our binder viscosities over here, obviously that's increasing the higher temperature range, but it's starting to raise up that lower temperature range. Again, obviously we don't have quite the same low temperature issues in Australia as they see over in the US. There's also, I guess, some adjustments that have been developed based on traffic loading. So that traffic loading, it considers both the traffic speed and also the traffic level. And therefore, based on, I guess, the temperature that's selected as a function of the climatic conditions, there's some additional adjustments that are required based on the level of trafficking in terms of design ESALs, but also in terms of the likely traffic speeds that particular section is likely to see. So if we're considering a lot of standing traffic, which is where the average traffic speed is less than 20 kilometers an hour, typically we need to bump our binder grade by 2 grades, and so that's essentially 1 grade is an equivalent of raising that high temperature by 6 degrees C. So bumping by 2 grades is bumping by 12 degrees C. If we're considering slow traffic, and so slow traffic is typically between 20 to 70 kilometers an hour, we need to bump our binder grade by one grade, which is 6 degrees C. Whereas if we're considering what's called standard traffic, where the average traffic speed is greater than 70 kilometers an hour, the only time that we really need to consider to bump the binder grade is where we've got a very high design traffic, so 30 million eSALs plus. So the next thing I'm going to talk about a little bit is the binder's sensitivity to temperature. So if the temperature grade is increased by 1 grade, what we're essentially saying is that the stiffness of the binder will approximately double. So a PG 70 binder will be roughly twice as stiff as a PG 64 binder at that temperature of 64 degrees C, and therefore a PG 76, which is 2 grades higher, will be around 4 times stiffer than a PG 64 binder at the temperature of 64. And as I mentioned before, we have to consider that bituminous binders are very sensitive to traffic speed, being viscoelastic in nature, and therefore the traffic speed affects the binder stiffness. So if we consider vehicles moving at 50 kilometers an hour, a binder will have an apparent stiffness, a much lower apparent stiffness than it does when the traffic is traveling at 100 kilometers an hour. So a mixture containing a PG 70 binder in a pavement with traffic moving at 50 kilometers an hour will have roughly the same stiffness as a mixture containing a PG 64 binder with traffic moving at 100 kilometers an hour. So by increasing the high temperature grade of our binder, we can offset against the effect of lower traffic speeds. Right, there are a number of devices used in the Superpave performance grading system in order to characterize our binders. The first one of which is the dynamic shear rheometer, which is used to measure properties at high and intermediate temperatures. So essentially it's a device where we have a static plate and a moving plate, and we sandwich our bitumen in between. We apply a rotation to the top plate, and then we measure the response of our bitumen to that application of load. Using that device, we can get some information about both the rutting performance and the fatigue cracking performance of our bituminous binders. The second piece of equipment that we need to consider is a rotational viscometer, which measures the properties of bitumen at high temperatures. So when I'm meaning high temperatures, I'm talking about asphalt mixing temperatures. So this time we're essentially taking some kind of cup filled with bitumen where we have a spindle that's lowered into it. We rotate that spindle and we measure the reaction of the spindle to the viscosity of the binder as a function of its temperature, to understand how viscous it's likely to be or how it performs at high temperatures. Then there's a couple of devices that are very specific to understand the low temperature properties, so not necessarily so applicable to Australia, and those are what's called a bending beam rheometer, essentially making or casting a beam of the bituminous binder, subjecting that to a low conditioning temperature, and then bending it and understanding its reaction to that bending force. The second device is called a direct tension tester, where again we're making a tensile blank of bitumen and then applying a tensile stress or strain to that at low temperatures to understand the performance. And again, we need to be considering how or the aged condition of our binders relative to where they need to be performing. So in terms of rotational viscometry testing, this tends to be applied to binder with no aging, so to simulate the during construction viscosity or mixing viscosity. Then we need to be looking at the rutting, and so again we might be considering that in an unaged state or applying rolling thin film oven aging to the sample, so simulate the construction and or manufacture and compaction and laying of on the properties of the binder. Then when we're considering fatigue cracking, we need to start to not only apply the rolling thin film oven aging, so the short-term aging, but also to start to consider to apply pressure aging in a pressure aging vessel to simulate the long-term aging of a binder. And again, when we characterize the low temperature cracking, we need to do that on binder that's gone through the RTFO aging and then through the PAV aging as well. The next thing I'm going to touch on briefly is aggregate selection. So aggregate characteristics are important parameters in making HMA perform well. So we need to make sure that we're using high quality aggregates, and we need to be trying to use our aggregate selection to overcome permanent deformation. We also need to be considering where in the asphalt layer they're being used. So typically we might be able to, for example, limestone aggregates tend to polish more than, say, granitic or basaltic aggregates, and therefore we wouldn't consider limestone aggregates in wearing courses. We also need to consider based on traffic level and traffic speed. Also, we might need to be considering in terms of, say, moisture susceptibility. So often we consider that granitic aggregates might be more susceptible to moisture than limestone aggregates. So that's another consideration to be made. But in the Superpave system, the aggregates are specified via aggregate grading restrictions. And there's some different types of requirements. So there are what are called consensus properties, which are required and can be measured. So those include coarse aggregate angularity, the fine aggregate angularity, and also the amount of flat and elongated particles and the clay content in our aggregate. And then there's what are called source properties, and these are properties that aren't necessarily clearly defined in terms of absolute limits, but there are considerations that still need to be made in order to make sure that our resultant asphalt mixture performs well. And so some of the examples of those properties that we need to keep an eye on are the toughness, the soundness, and the amount of deleterious materials within our aggregates. And again, obviously in Australia, we've got a number of standards and specifications around aggregates for use in asphaltic applications, and they take into account these consensus properties, but also the source properties. So the next thing I'm going to go on to is to talk about material selection in terms of gradation. So this chart on the right-hand side is essentially a grading chart where the x-axis is the sieve size, but raised to a power of 0.45, and the y-axis is the percentage passing, and the gradation curve with the sieve size raised to a power of 0.45 has been found. If you plot out a straight line between the 0 point and the maximum nominal aggregate size, or the maximum size, sorry, that straight line will provide you with the gradation required to meet maximum density. So the maximum size is one sieve larger than the nominal maximum size, and defining the nominal maximum aggregate size is essentially that's one sieve size larger than the first sieve to retain more than 10% of the aggregate. So there's a few other things that we need to be mindful of when we're selecting our gradation. The first thing I'm just going to mention briefly that at one point there was what was called a restricted zone between the 0.3 millimeter sieve and the 2.3 millimeter sieve, and essentially there was a consideration that we just need to be a little bit careful around there, that certain gradations that pass through that restricted zone could lead to sort of humped gradations, and potentially possess too much fine sand in relation to the total sand, which might lead to a tender mix and reduce resistance to permanent deformation. It's a little bit of a grey area, and I think the general consensus is that people aren't so worried about the mix, the restricted zone these days. But the main thing is to make sure that you're meeting property requirements after you've selected your gradation and prepared your optimum mix design. But the second thing that we need to consider are some minimum and maximum values on certain control size or control sieve sizes. So there's a number of control sieve sizes based on the nominal size of the mixes, and then there's requirements therefore that the mix design falls between those maximum and minimum values at those control sieve sizes. So the next thing I'm going to talk about is the design aggregate structure. So the design aggregate structure is the term used to describe the cumulative frequency distribution of the aggregate particles. So essentially the gradation of the mix, and a design aggregate structure that lies between the control points, but potentially avoids that restricted zone, meets the requirements of Superpave with respect to gradation. So some examples are shown here. So we've got, this is the restricted zone. So ideally we want to try and avoid that. And then we have control sieves at 0.075, so the 75 micron sieve, then at 2.36, and at the maximum sieve size and the nominal maximum sieve size. We have some, so if we can meet those maximum and minimum requirements, and ideally get underneath our restricted zone, then our design aggregate structure will meet the Superpave requirements. This table just shows some of the what are called Superpave mixture design designations in terms of well, their designations, so a nominal size, and then so essentially what they're based on a nominal maximum size of aggregate, and their maximum aggregate size is one sieve size larger than that. So when we design our aggregate structure, we want to essentially design a blend. So there's a preliminary determination that needs to be carried out, and we can carry out some trial blends mathematically by combining gradations of the individual materials to perform into a single blend, and then we can compare those against that allowable specification that I showed on the previous slide. So typically we would recommend to look at developing at least 3 trial blends to see how they match up with the Superpave gradation requirements. And they're obviously based on, these blends are based on combining the coarse aggregates, the intermediate, the manufactured fines, and the natural fines. So the next stage of the process is to design the binder content. And this is where we get into compaction with the Superpave gyratory compactor. And there's a number of criteria which have been defined during that compaction process that we want to ideally try to meet. And those are the N initial, N design, and N maximum. But the key contraction parameter in all of this is N design. So this table on the right hand side is just showing the number of gyrations that are required to make sure that we're meeting the requirements dependent on the design E-cells for our asphalt mixture. And therefore we need to make sure that we're meeting, and I'll show it on the next slide, I think, some density requirements that need to be met at each of these different compaction, N initial, N design, and N maximum. So these criteria that need to be met in terms of the compactive effort. In fact, it's probably on the slide afterwards. But essentially the Superpave mixture design criteria is based on mixture volumetric requirements. And so typically we're designing at 4% air voids. There's a few other definitions as well that need to be considered. So voids in mineral aggregate is the total of the air voids plus the bituminous binder. And then there's this other term which is voids filled with asphalt, or in our terminology, bitumen. So essentially it's the percentage of bitumen in the mix. And And we also need to be considering the mixture density during compaction at N initial and N max. And there's a number of different design requirements based on Superpave for voids in mineral aggregate and voids filled with bitumen based on either nominal aggregate size in the case of voids in mineral aggregate, or design ESALs in terms of voids filled with bitumen. There's also a requirement for the dust proportion to be between 0.6 and 1.2, and we need to make sure that we're meeting our moisture susceptibility requirements. So in terms of our design bitumen binder content, as I mentioned before, in terms of N initial, we need to make sure that at that point the density is less than 89% of the maximum density. At the design end design, we want our density to be 96% of maximum density, i.e. 4% air voids. And this N max number, we want this to be less than 98% of our maximum density. So this is an indication of densification under trafficking. Again, the main requirement that we're looking to meet is this N design. So a design binder content is estimated based on experience with similar materials, or by estimating the effective specific gravity of a blend using calculations for aggregate effective specific gravity, the volume of binder that the aggregate absorbs, and therefore the volume of effective binder, and then estimating the trial binder content. So when we go through our compaction process, we need to vary the amount of the bituminous binder in the design aggregate to obtain an acceptable volumetric property, to establish the material criteria. So that's based on our estimated binder content, and then we need to look at the estimated binder content plus or minus 0.5%, and also the estimated binder content plus 1%. And this gives us an indication of the sensitivity of the design properties to changes in the binder content during production. So we need to be meeting that 4% air voids. We need to be meeting a minimum of 13% voids in mineral aggregate. We need to be having voids filled with bitumen of 65 to 75%, a dust proportion in the range of 0.6 to 1.2, and an initial compaction density of less than 89% of the maximum density. So on the right, it's just showing some of these requirements as a function of, so the effective binder, or the binder content, as a function of air voids. And then in terms of voids in mineral aggregate, in terms of the dust proportion, so obviously the higher the dust content, the more binder that we need. In terms of air voids, the more binder content we include, the lower the air voids becomes. but in terms of voids in mineral aggregates, there's I guess an inflection point, because the voids in mineral aggregate is considering both the bitumen and the air void content. And then there's some requirements in terms of the percentage of maximum density at N initial. So we want to be below 89%. And again, as we reduce that binder content, so we get a drop in the likely density achieved at N initial. Right, the last thing we need to consider when we've gone through our process, so effectively we've gone through the whole process now, we've selected our bitumen, we've selected our aggregates, we've selected our gradation, and now we've determined our optimum binder content. So in this case, this graph is showing that our binder content is around 4.9%. Now we need to check the moisture sensitivity of our asphalt mixture. So the moisture sensitivity test is undertaken, it's essentially ASHTO T283. So what we're doing is we take our optimum mix design, we compact it to air voids at 7% air void content. We make two sets of or subsets of samples. One set is our control, which is unconditioned, and the second is our conditioned subset. So we select our subset so that there's minimal variation in the average air void content between the two. The conditioned subset is then, they need to be vacuum saturated to a range of 55 to 80% saturation. And then that's followed by an optional freeze cycle and 24 hours in a hot water soak at 60 degrees C. So on the right hand side we can see the vacuum saturation system, and underneath that is the water bath that's used for the conditioning. After they've gone through that process, well, essentially we're testing the unconditioned batch and the conditioned batch in indirect tensile strength, and the moisture sensitivity is determined as the ratio of the tensile strengths of the conditioned subset divided by the tensile strengths of the control subset, and the minimum requirement to pass this is 80%. And so again, this is very similar to some of the moisture sensitivity requirements in Australia. In Australia, typically we quite often, depending on the mix type and its end use, we stipulate a minimum requirement on the conditioned tensile strength as well. So in this case, we have a tensile strength ratio of 82.7, and therefore it's achieved that moisture sensitivity requirement, and therefore we've now agreed that we've got a suitable mix through the Superpave design process. So I'm just going to give a quick summary. So what have we learned? We've gone through looking at components of an asphalt mixture. We've looked at traditional mix design methods, or in particular the Marshall mix design method, talked through some of the advantages of Superpave, and then I've run through the fundamentals of a Superpave mix design in terms of material selection, paying particular attention to the Superpave performance grading for binders, then the design of an aggregate structure, and then going through as how we design the binder content, and then looking at that moisture sensitivity requirement. As I mentioned before, this is part of 2 webinars. In the second webinar, we will go into a little bit more detail on the Superpave mix design method, and in particular look at some examples. So how do you design open graded asphalt through the Superpave process, and also look at methodologies for designing EME2. So I guess alternatives to Superpave, again, in terms of mixed design methods, given that EME2 was developed in Europe and again follows slightly different design procedures over there. And the final thing that I want to look at next time is understanding a bit more about asphalt mixture performance testing to support Superpave. So we've talked a little bit about some of the performance requirements in terms of the binder. Obviously, it's important to understand permanent deformation and fatigue requirements and also that moisture sensitivity. But based on some of the binder testing, it means that potentially some of the mixture testing, such as the fatigue performance and the low temperature cracking requirements, aren't essential to perform, but I'll go into that in a bit more detail next time. So that ends me running through the content today.